Good afternoon. You guys excited? Yeah? Let me hear something here. Okay, good. It's good. It's the first day of reInvent, and there's always a lot of energy. It's a nice big crowd, so I appreciate you guys all coming here and spending the afternoon with us. It's a little hot, so I can take this off. My name is Mehul Shah, and I'm the engineering manager for AWS Glue. And today, I'm going to be speaking to you about how you can build analytics pipelines with Glue. And then I have with me my co-presenter, Arup Ray, who's the VP of Engineering at Realtor.com, and he'll be talking about the success that they've had in putting Glue in production in their organization. So quickly, I'm going to give you an overview of Glue to start. And this is a 300-level presentation, so I'm actually going to get into some of the details on the things that we've done over the last year and a half to improve Glue, as well as the new features that we've added. And then I'll hand it over to Arup to talk about how they've put it into practice. All right, so let's get into it. A year ago, we introduced Glue to the family of AWS services. We introduced it as a fully managed serverless extract, transform, and load service, or ETL for short. Now, I know that's a mouthful, and there are plenty of other ETL services out there today and were at the time. So why did we build it? Well, it turned out that even though there's so many ETL services out there, there were very few that were focused on you, our customers, that were developers in the audience. We as developers found that the other tools weren't really there for what we needed, and you guys agreed. And so we kicked this off about a year ago. At that time, we had about thousands of customers and running thousands of jobs daily. And this was the slide that I used last year describing the lighthouse customers that braved the early days of Glue with us, both feet in first. Today, we've grown much beyond that. This is just a smattering of customers that we have in production today. There's a lot more. And you, our customers, have helped us grow. On the left-hand side, what you see is the number of jobs and crawlers that run on a monthly basis since we launched in Glue, and you can see that their workloads have been exploding. And on the right-hand side, what you see is the number of regions that Glue is in. We're at 12 regions today, and many more to come by the end of the year. So besides just running Glue and making sure that it scales for you and fixing all the bugs, we've been busy listening to you as well. We've built a number of major features over the last year, not just adding incremental things, but brand new things that make it easy for you to run your ETL jobs. We do a lot more of the undifferentiated heavy lifting that we always intended to do. So let's take a look at what Glue actually looks like. It's got three main components, okay? The first component is a data catalog. It's a metadata store, a centralized metadata store for all your analytics data in AWS and beyond. With catalogs, you have crawlers. We provide crawlers that actually open up the data sets that you have, crack them open, extract the metadata, extract the structures, extract the organization, and then actually load all of that metadata into the catalog for you, so you don't have to do it. The catalog is Hive Metastore compatible, so other services, analytic services like Redshift and Athena and EMR, can integrate with the catalog to understand what they're querying and actually go after the data and query it. So you can use it across a number of different services. Another major component for Glue is its serverless job execution system. Okay? At the core, and this is a key value proposition that we have, at the core of our job execution system is an open platform, Apache Spark, that runs all of your jobs. You submit your ETL jobs written in Python or Scala. Just give us the job. We provision all the machinery that's necessary to run those jobs. We configure the networks, we spin up the machines, we shut them down, and all you do is pay for the time that the job ran. Okay? And if you don't like writing code, no problem. We actually give you tools that, based on the data that you have in the data catalog, will automatically generate the code that you need to do transformations from one source format to another, one source to another destination. The third component of Glue is its orchestration system. Okay? Here, what we give you is a system that allows you to stitch together multiple jobs to accomplish a larger task. You can stitch them together in a linear fashion, or any DAG, any arbitrary directed acyclic graph of jobs that you want to put together. We allow you to monitor this. We check for failures. We do retries. And we also have ways of integrating the orchestration system with external services within AWS and beyond. So that, in a nutshell, is what Glue was offered as and is continued to offer as. But beyond just the ETL components, our customers, you, have used Glue in ways that we didn't anticipate to begin with. So we originally gave you the APIs that were needed to actually stitch together your own notebooks sitting on your laptops or your desktops to the underlying serverless infrastructure that we had. We found you using that a lot. And so what we did is we actually added integration with Amazon SageMaker notebooks. And so now if you want to do data science and data exploration, you can do it seamlessly without ever spinning up a server, completely managed by AWS. And here's what you're saying, okay? So there are things that we anticipated that you would do. Here's what's emerging based on the uses that we see for Glue. One major use case that has emerged is the one around building and managing data lakes. Data lakes are a centralized repository of structured and unstructured data that companies are putting together to manage all of their data and analytics in one place. We see many of our customers managing this data with AWS Glue and then analyzing that data with one of many different analytics services in AWS. They use it with Amazon EMR to query the data in Hive or Spark. They use it to load data into Redshift and run SQL queries. Customers are also telling us that Glue is cost effective. It's pretty simple to get a small team of engineers to get this up and running at the fraction of a cost of what it would take with a traditional ETL tool. They're also telling us that Glue is fast, faster than a lot of the traditional ETL tools. So how did we get there? Well, we've been busy. We've been busy in making improvements in three major areas. The first is around scalability and performance, and this is the scalability and performance of the crawler and the ETL job system. And I'll dig into that next. The second thing we've done is we've added a number of APIs and to open up what's going on under the hood in our jobs. We're actually revealing metrics on how the jobs are run so that you can profile them and optimize them. And then finally, we've added a number of interoperability features to make Glue work well with all of the other services outside of Glue. And today, I'm going to be announcing a new job type called Python Shell that actually enhances the interoperability that Glue provides. All right, so let's get started. Let's talk about a simple example that I'm going to be using throughout the talk. Okay? Imagine you have some data. Let's say it's data like the GitHub public timeline data. It's the data that's publicly available about all the events that GitHub sees on the public APIs that they have, and they make this publicly available. What a lot of our customers are doing is taking this kind of data. These are just log events and so on, and they're organizing it in S3 inside of buckets. And instead of putting all hundreds of thousands or millions of files into one bucket, what they're doing is organizing it into directories, hierarchies. We call them Hive-style partitions, but really they're just file system hierarchies. And the reason they do this is so that they can get to some subsets of the data very quickly. So it's easier to discover the data sets that they care about. And what they do is they take the raw data and they transform it somehow, either reducing it or just changing the format into something that's optimized for analytics on the right-hand side. In this particular case, we're maintaining the same hierarchy. The hierarchy here is in terms of years, month, and day, but you could use any other hierarchy, like region, for example. And the format and the target format is Parquet, which is typically optimized, typically useful for analytics. So what happens if you try to crawl the source data here? Well, here's what it looks like. Very quickly, what you can see is that the crawlers pick up the top-level attributes in your data, as well as all the various nested attributes that you have in there. In this particular case, there are hundreds of nested fields in there. You don't have to figure that out. It figures it out for you. It also keeps track of how the files are grouped into hierarchies in terms of their partitions, and it does that automatically and discovers it and registers it in the data catalog. Well, over the last year, we've been hard at work making this much better and more scalable. Crawlers are now 7 times faster than they used to be on average. We can run over nearly 900 million files in a day. Definitely can handle hundreds of thousands, if not millions of partitions. And of course, your mileage is going to vary depending on the size and complexity of the data, as well as the partition structures that you have. This is what Glue ETL scripts look like. These are the generated scripts that come out directly from the service. On the left-hand side, what you'll see is a high-level overview of the script and the transforms that are being run. On the right-hand side is the actual script that you can either just run or take a look at, debug, profile, modify, do whatever you want with, okay? There's a lot of boilerplate stuff inside of the script, as well as various transformations that are automatically put in there to do a lot of the cleaning and transformation to get into the target format. To understand what the script is doing, it's important to actually understand how the system is built. So Glue is actually built on top of an Apache Spark core, okay? At the bottom in Apache Spark, what you get are RDDs, or resilient data sets, or resilient distributed data sets. These are basically data structures that allow you to put data in them and then run operations over them in a fault-tolerant way. Apache Spark itself has built an additional data structure on top of this called data frames, and data frames are optimized for doing SQL-like analytics. Okay? That's what Spark is. What we've done is we've actually added a parallel set of infrastructure or code, libraries in particular, where we have a parallel data structure called dynamic frames that are optimized for ETL. And then a bunch of transforms on top of dynamic frames that make it easy to do the data cleaning and restructuring that you need. So let's dig into that a little bit and see how that helps. Data frames and dynamic frames. Data frames are the basic core data structure for Spark SQL. They're like structured tables. We all know what tables look like. You need a schema up front. Each row has the same structure. And when you know that every row has the same structure, what you can do is you can optimize the layout of that structure for SQL-like analytics. It works really well, makes it go super fast. If, on the other hand, what you're doing is ETL, this structure actually gets in the way, especially if you're looking at unclean, incomplete, semi-structured data that's often coming out of logs, for example, Avro data or JSON data, or things that just didn't anticipate recording, but you recorded, and now you've got to go analyze it. So what dynamic frames do is that they actually store the structure of each record with the record itself. So every record can be different from the previous. There's no need to have a schema up front. There's no need to do a pass over the data to compute the schema before you put it all in. You simply start sucking in the data and start running operations over it. And that's why it's useful for ETL. It's going to go slower for SQL, a lot slower, but that's not what it's intended for. And these things are not competing with one another. They actually go hand in hand. They're complementary. You can take a dynamic frame and turn it into a data frame, and vice versa. So how fast are these things? Well, when we initially started, they were good. We were really designing it to do one pass over the data instead of multiple passes over the data. But they're now even gooder. They're much faster than they used to be. About 4 times faster since we first launched the service. You can run over a terabyte in under 1.5 hours with a 10 DPU cluster. DPU is our unit of scaling. It's our unit of capacity. It corresponds to 4 vCPUs and 16 gigabytes of memory. Okay? And of course, if you increase the number of DPUs, this will go faster. If you reduce the number of DPUs, it's going to go slower. And the runtimes are going to vary based on the data formats you're reading and writing. In this particular case, we were reading JSON and writing Parquet as an example. And of course, it's going to vary depending on what you're doing in the script and the complexity of that script. Here's another cool thing that we've done with dynamic frames. If your data is organized into these Hive-style partitions, you don't need to scan over your data every time you run a query. If you only care about a subset of the data, let's imagine you only care about 1 month's worth of data or 1 day's worth of data, you can just basically specify, you can specify which month, year, or which partitions you care about with like a where clause, effectively. That gets pushed down into the infrastructure. We only read over the files that are necessary and then scan those. So on the right-hand side, what you see here is an experiment where we run over different number of months that are covered in that timeline, and you see that the performance scales linearly. What this shows you is that there's very little overhead in being able to push these predicates down. The predicates are the filter clauses. All right, so that's the scalability of performance of our system. We continue to push on the scalability of our system and make it better and bigger and faster. But that's just not enough. Turns out that you give us a script, sometimes it just doesn't perform the way you expect it to. Okay? This was especially frustrating when we first started, where you got very little information other than it worked or it didn't work. And so we listened to you. We opened up what was happening under the covers, or under the hood, and we're now sending back metrics that tell you how the job is performing. To understand what these metrics do, it's important to understand how Glue actually does its execution. Glue's execution is based on Apache Spark. Okay? What Glue does is it takes these Apache Spark scripts, they're written in Python or Scala, and it sends them to the driver. The driver then basically breaks up these scripts into stages. Stages are basically parts of the program that need to be run one after another. Each stage is then broken up into quote-unquote shards or partitions. It's different from the Hive-style partitions I was talking about earlier, but just shards or partitions. You take a table, for example, and break it up into 100 partitions, or take a table and break it up into 1,000 partitions, just depending on how many partitions you have. It's a data parallel processing system, so these shards can be processed all at the same time in parallel. For each stage and each partition, Spark has a task. And the job of the driver is to allocate these tasks to physical nodes or physical executors that actually run these tasks. So the job here for the driver is to take these tasks that are all kind of ready to be executed and pack them onto executors as soon as they come in. Okay? So that's the scheduling that it does. For every DPU that you ask Glue to run a job for, we allocate 2 executors. It's just a standard mapping that we have. And what you'll notice here is that the throughput of our system, the sort of optimal throughput of our system, is limited by the number of partitions or shards that you have in your program, okay? Or in your data set. So how do you run these metrics? Well, you simply go to the console and say, turn on the metrics. You can do this also through the CLI or the SDK by passing in a flag, -enable metrics. Pretty simple. We actually derive our metrics from the underlying Apache Spark metrics that the cluster gives us. We have metrics on the driver as well as per executor. We return aggregate metrics as well as instantaneous metrics. As the job is running, we send those metrics to Amazon CloudWatch on a periodic basis, roughly every 30 seconds. And the kinds of things that we send back are memory usage, the amount of data that an executor read or wrote, the CPU load on a driver or executor, the amount of bytes that were shuffled or sent back and forth as they were communicating among executors. We also send back the number of quote-unquote needed executors. These are basically the amount of tasks that are in flight that could be scheduled if you had those number of executors. So it gives you an idea of how far you can scale the system for your particular job. So let's take 2 examples on how these metrics can help. A simple example here is when you're processing lots of small files with just say traditional regular data frames. This happens, for example, if you're taking streaming data and you're collecting it, say, through Kinesis or some other streaming system and storing these things into files. Often these files will be, some portion of time, so they'll be 0 or 0 length or small files, and then suddenly you'll get a burst of activity, and then they'll get small again. If you have hundreds of thousands or millions of files, it turns out the way data frames work, that there's a single task per file, and there's metadata or overhead that you have to keep track of, the driver has to keep track of per task. And so what ends up happening is that all this metadata gets sent to the driver can't keep track of it, and immediately what you can see on the graph here is that the driver memory goes beyond a critical boundary, and then you run into an out-of-memory error. You can see similar things on executors when executors run into out-of-memory errors. And you can use this to go and figure out where that out-of-memory happened and why it might have happened. In this particular case, it's because the driver was overwhelmed. Well, no problem. Turn on dynamic frames instead. We can actually read all the same formats that Spark can, data frames can. And dynamic frames have this ability to automatically group lots of files into fewer tasks. That automation allows the driver to keep the number of tasks small enough so that it fits into memory. And your job now finishes actually rather than just breaking and shutting down with an out-of-memory error. If you don't like the way dynamic frames does the grouping, you still run into out-of-memory errors. You can adjust the grouping parameters yourself by just going into the code and playing around with it. Another example is optimizing parallelism with Glue metrics. In this particular case, what we're doing is we're processing large bzip files. And bzip is a format that's splittable. What that means is that you can actually index into a bzip file, into the middle of it, and read some portions of it. So dynamic frames will automatically kind of index into it, depending on how many executors are available. And in this particular case, there's 2 metrics that are worth noting. There's the red line. This is run with 10 DPU. That tells you the maximum number of executors that the system has. You said, I want to run this thing with 10 DPU. You get something like 17 executors. There's some number of executors that are overhead. And the green line is the instantaneous number of executors that could be used at any particular time in the program. And you can see it going up and down. The interesting thing here is that when you run it at 10 DPU, there's actually a lot more executors that it could use that are just waiting. There's sort of tasks that, executors that it could use because there's a bunch of tasks that are just waiting to be scheduled. And so you could actually get the system to go run a lot faster if you bumped up the number of DPUs. So if you bump it up to 15 DPUs, now all of a sudden the number of active executors, the number of executors that are actually running, with matches or tracks very closely the number of potential executors that you would need to run the program. So going beyond 15 DPU isn't going to get you additional performance improvement. The point here that I'm trying to make is before all these metrics were there, it was just basically trial and error. You'd run a job, you'd waste some cache, you'd run it again with more DPU, you'd see if it helped. If not, you'd eventually do a binary search and settle on where it ought to be. And then who knows how things would change as your data sets changed. Now you actually can see what's going on underneath and adjust it on the fly as you need. All right, so that's some of the cool stuff that we have. There are other metrics and other use cases around how you can keep track of how much data is sent across the network and so on to debug other kinds of problems that you run into when you're running jobs. But I want to switch focus now to talk about interoperability. First, let's talk about orchestration. So when we launched a year ago, we said, OK, you got jobs, you have triggers, You can compose jobs using triggers. So when a job completes, you trigger another job, or you can trigger another set of jobs, and so you can create a DAG of jobs and dependencies and build very complex flows. So from our experience, people are used to building lots of complex flows to get complex tasks done. For example, handling your daily analytics pipeline typically involves dozens of tasks, right? In practice, we didn't give you enough controls to actually build any complex workflows. What we saw were that customers were transforming data sets from one format to another and running crawlers to keep track of what was added and what was deleted from the source, and then when it gets to the destination, what was added and what was deleted. And there was no good way to actually stitch this stuff together. And so what they did was they used schedules. They used to say, okay, every 5 minutes I'm going to run a crawl. I'm going to hope that in those 5 minutes I get all the new data that we saw. Crawls typically take 4 or 5 minutes, so 5 minutes later I'm going to run a job, and when I run that job typically takes 10 to 20 minutes, so 20 minutes after that I'm going to run another crawl, and then I'll be ready to send my reports to Athena or Redshift and run those reports. And they put a lot of slop in between to deal with timing issues. And of course, if you had anything that went poorly, God help you, because you couldn't fix this, right? So we added a lot more building blocks to orchestration. So in orchestration, we have sort of 3 main entities: crawlers, jobs, and triggers. That's what we started with, and we had schedules. We added a lot more event types and the ability to integrate with external services. We also added more control flow mechanisms, in particular more complicated conditions that tell you which direction you can send the data flow. And we also added more ways of controlling how to deal with delays and timeouts in jobs. So to integrate externally with other services, we actually send notifications when a job is complete or crawler is complete into Amazon CloudWatch. We publish these notifications, which will then trigger Amazon CloudWatch events. And you can use those events to then control downstream workflows. We added 2 new condition types, any and all. Any is basically an or. A bunch of upstream jobs get finished, and if any of them finish, you can then trigger the trigger, which then runs a workflow for a downstream job. All is basically an and. All of the upstream jobs have to finish before the trigger condition is met, in which case you can then run the downstream workflow. We also added states for failures for jobs, not just completions, because we all know that jobs do more than just complete. So we notify you when things fail, and there's an event for that. When you purposely stop a job, when you hit a timeout, we now allow you to control the job timeout value before it was just set for you. And we have a new type of notification where you can set a delay. I expect this job to run for 15 minutes, and if it goes beyond that, please notify me so that I can run another workflow to compensate for the fact that this is running too slow. So you can do a lot of things with all these new features that we've added. Most importantly, you can run the standard workflow that we hope that you would, that we saw coming up. So as new data arrives, you can trigger a Lambda. The Lambda will then start the crawl. After you start the crawl, it runs. When it's finished, it'll publish an event to CloudWatch, which triggers another Lambda, which can then run another job. And then you can kind of stitch this together with CloudWatch, Lambda, another crawl, any subsequent analytics that you have to do, and then get your workflow done in a tight deadline in lockstep, rather than hoping that it gets done. But this is just a very simple example. Now you can actually build much more complex flows this way. Another thing that we found that you were doing, okay, all of this talk is about what you guys were doing and how we're learning from you, if you haven't figured it out by now. But another thing that we found that you were doing was that you were using Python shell. You were using the Python components of Spark to actually control ETL and other operations outside of just Spark. And this seemed very puzzling, right? It's like, why are you doing that? Well, it turns out not all of your ETL in a very complex flow always fits into the Spark containers, right? The kinds of things that you want to do with Spark. Sometimes you want to run a SQL query on Redshift. Sometimes you might want to run a SQL query on Presto and EMR or Hive. And the only thing that you had as a primitive with Glue was a Spark cluster. So we said, why don't we give you something where you don't actually have to pay for the cost of a cluster, even though it's not doing anything for you. So instead, we're just giving you a Python shell. It's a new job type. It's a new cost-effective ETL primitive for small to medium-sized tasks where a cluster is just overkill. Okay? People can use this for running SQL-based or controlling SQL-based ETL. So running queries on Redshift, making sure that they run successfully, and then running the next, and so on. You can use it to build things that are hard to build inside of Spark, like custom connectors for third-party services that have complicated, API semantics. For example, if you want to go get data out of SFTP, or if you want to go get data out of some, web service, some software as a service app, and whatnot, to get that data into S3. And then you can coordinate that, this Python shell with all the other orchestration features that we have. The other thing that you can do with Python shell is run a bunch of medium-sized ML tasks. It turns out that Python shell fits that sweet spot for these types of tasks. Kinds of tasks where you kind of need a sizable memory, but not an infinite amount of memory, and you need like a bunch of compute, but not an infinite amount of compute. It happens all the time. And so here, here's sort of a perfect a tool for that. Let me tell you a little bit about the specs for Python shell. Python shell comes with basically a standard Python 2.7 environment. I know you're going to ask me, when is Python 3 coming? It's coming soon. Okay. But we'll be releasing Python 2.7 first. It comes with a bunch of goodies. Boto 3 is there so that you can hit a bunch of AWS APIs. You can use the AWS CLI. It comes with standard libraries like NumPy, SciPy, and Pandas for doing scientific computing, machine learning. A bunch of libraries to connect to Postgres and Redshift and MySQL and so on. Here's some of the cool things about Python shell. One, even if we don't have one provisioned and ready for you, if we have to provision it from scratch, it still takes only 20 seconds. Much, much cheaper than spinning up a cluster. We still support the configuring to attaching to your VPCs. And there's absolutely no runtime limit. You can run it for a day, a week, a month, a year. It's up to you. Okay? Unlike other systems that we have. It comes in two different sizes. The 1 DPU size is 4 vCPUs and 16 gigabytes of memory. This is for sort of those medium-sized tasks. And then 1/16 DPU, which gives you 1 gigabyte of memory. This is for your control plane or control flow type tasks. It's 44 cents a DPU hour in terms of pricing. It's the same pricing that we charge for all of our other job types. It's per second billing. But here's the most important thing. It's a 1-minute minimum, okay? Not a 10-minute minimum. So really there for a lot of your lightweight tasks, you're definitely not paying for the spin up or the tear down time, but you're also not paying any overhead for very short jobs that you have to run. And so this will be coming soon, right after reInvent. It'll be available for all of you to try it out. Here's a simple example of what you can do with Python shell. Collaborative filtering. So the problem here is, how do we take a bunch of reviews that we have from Amazon? You can actually go get this off the web. These are the Amazon.com retail customer reviews for a variety of products across the website. It says as of 2013, I believe, so it's a little old. And we took all the reviews from the video category, and based on those reviews, if you get a new customer, how do you decide what to recommend to them? Well, there's a lot of different ways to do collaborative filtering, but a popular way is to actually compute a huge matrix. Okay, and this is why this is a good example for Python shell. This matrix is, in this particular case for just the video category, is the customer product matrix. Every row is a customer, every column is a product, and every entry is the rating that that customer gave for that particular product. Right? Now, this is a very noisy and large matrix, and what you want to do is sort of boil it down to its essence. Really, the major components of where all the power or the information in that matrix is, and separate that out from all of the noise that's in that matrix. A common way to do that is to take that matrix and create a low-dimensional or low-rank approximation of that matrix, and then with that low-rank approximation, use that approximation to predict what a new customer might want or could want to would want to see from the product list that you have. The important point here is not the machine learning and the transforms, the SVD is the transform that does that, singular value decomposition. The important point is that the SVD requires a bunch of memory and it requires a bunch of CPU and some time to iterate over that to get you the answers. And in this case, you can actually just very quickly get that up and running using the SciPy sparse matrix library that comes packaged with Python shell and the SVD computation that comes packaged with Python shell. There's basically 4 steps here. We used Redshift to copy the data into a Redshift table, run a SQL query to extract the customer product pairs. We loaded those pairs into a matrix and then ran the SVD. The Redshift SQL queries took less than 20 seconds. It was nothing, really. And then, the computation is where all the work was. And this is for calculating a 1,000 dimension or 1,000 rank matrix. The matrix size, original matrix size was 200K by 400K. The point here is that it took 70 minutes or about an hour to run this. And the other point is that it cost 60 cents, less than $1 to actually do all of this. And so you really don't need a cluster. You just need a medium-sized machine to go and run this on, and that's what this job type is for. There's so much more that we've added to Glue. I just don't have the time to go over them. But there are 3 important things that I'd like to touch upon. One is that now we have native support in dynamic frames for DynamoDB tables. What this means is, with a single line of code, you can read a DynamoDB table in parallel into a dynamic frame, turn it to a data frame like I talked about earlier, and then run your SQL queries over that data frame. So it allows you to run SQL over DynamoDB data in situ. You don't have to go dump it to S3 or anything like that. Just run a SQL query. Try it out. It's already available. We have encryption for those of you that are really sensitive to how you store your data and how you run your systems. We encrypt at the platform level inside the cluster. We encrypt the communication that's going back and forth from executors. And we also encrypt the data at rest with customer-managed AWS KMS keys. We're also compliant with 3 different certifications right now: GDPR compliance, HIPAA, and BAA, and more compliance certifications are about to come. All right, so there's a bunch of related breakouts tomorrow and the day after, and I couldn't fit any more on the slide about AWS Glue. So if you want to dig into some of the things that I talked about, get into the details, try them out, I recommend that you attend. And with that, I'd like to hand it over to Arup. Thank you very much.
Thanks, Mehul. Good afternoon, people. My name is Arup Ray, and I'm the Vice President of Engineering at Realtor.com. And today I'm going to talk to you about how we use AWS Glue at Realtor.com. So Realtor.com is part of News Corp, and we call ourselves the home of home search. So our mission is to empower people by making all things home simple, efficient, and enjoyable. So when you're looking for the home that you want to buy, this is the place that you have to go. In terms of how popular the site is, we have the highest engagement. People have about 1.5 times the page views, 1.3 times longer visits, and it's a very motivated audience that's trying to buy a home. And in terms of raw statistics, we have about 63 million uniques every month, and 2 billion plus page views. So every click, every page view ends up in our data platform as a record. So you can well imagine the volume and scale that we deal with. For us, in the data analytics platform, we have moved completely away from our old data center-based SQL Server infrastructure into AWS. And almost all the data is today on S3. And if you think about it, when data shows up from sources, they are either showing up near real time through API-based integration, or people are dropping files, or we are extracting files. What we have done is we have carved out parts of our S3 buckets which serve as file drop, the way the file came in. We also have the archive region where we archive the files. Then we have the area from which we start our processing, and that's our raw data layer. From raw, we take it through different levels of curation. At the beginning, we have what we call the process data transactional. To make the data more accessible, we want to put it in a format where the metadata is known, where people can run queries. So what we do is, regardless of the way the data came in, we put it into a columnar compressed format. We put it into Parquet format, makes it very easy for us to query the data. And then from process data transactional, we take it to business data layer, where we put the business overlay, the business metadata on top of the data. And finally, if there are data sets that we have to feed other systems or reports, we aggregate whatever we need to do, filter, and create the access data layer. So what we have done is, as we go from raw data to process data transactional, we are trying to build a template-driven transformation. We do not want to have every data set that comes in have its own distinct pipeline, but we want a template-based solution so that instead of writing new pipelines, we are configuring new pipelines at runtime. So the problem is, how do we generalize the ETL process to handle these generic data sets and generic volumes that we get? How do we solve for patterns that we see over and over again? Things like deeply nested JSON attributes with rows in it, which needs to be exploded out, and finally, make the data easy for us to query. We were using EMR Hive as the basis of what we did, and a lot of the functionalities was coded as user-defined functions. So the challenges were, of course, we had to maintain the cluster for EMR, and the UDF code that we wrote and used definitely required a lot of maintenance over time. So if you think about the problem that we are trying to solve, you have raw data, and we allowed raw data in two different distinct formats: CSV with header, where we know the metadata, or JSON, where the metadata is embedded within the data. And what we are trying to do is convert it into process data transactional layer in Parquet format. And during this process, few things are happening. One is we are validating the structure of the input, the data types of the fields that are coming in. We are relationalizing the data. We are taking multi-valued columns and exploding them out into multiple rows in child table. We are also taking deeply nested JSON attributes and aggregating them up at the top level, and optionally detect duplication of records in the input set. So that's what we are trying to do. Final output would be in Parquet format. The way we do it today is the orchestration is being done from AWS data pipeline. For every data set, we have our own app ID. It kicks off our process on ECS. And on ECS, the first thing that our script does is it goes out and gets a configuration for this particular pipeline. Namely, what are the columns that we need to validate? What are the fields that require explosion? What are the fields that require compaction? Then we have another service called the last good key service that we have built, which keeps track of what was the last partition, last day, last hour, that has been successfully processed, so that the next time when the script is running, it knows to go to the last good key service for this app, find out where should I start from, and go from that point onwards. So once the state is done, then from Amazon ECS, the script goes and puts a soft lock on the source and the target so that another process running at the same time doesn't end up working together and against each other. Finally, the configuration in JSON format is parsed, and the template code gets filled in. This is where Glue starts its magic. It retrieves the data from the input partition based on what the last good key service said it should. It performs the data type validation on the columns that are prescribed in the configuration, performs flattening. It relationalizes and explodes the multi-valued columns into child tables, and it saves the result in Parquet format and writes it out to S3 again. So that's what is happening with Glue. Finally, we update our last good key service to say that, OK, one more partition got processed, so that the next time we run, we have the bookmark there. Finally, we use AWS Glue crawler to crawl the new data set that was just created, and the new partitions just become discoverable. Finally, we unlock both the source and the targets. So this is how we do it today. However, we are moving forward with a new way of doing things. So we are gradually moving away from data pipeline into Airflow to manage complex DAG-based dependency management. And instead of ECS, we kick that off in Python shell. So we are a beta user for that. And from Python shell, we do exactly what we used to do from ECS. Go call config service, last good key service, go and lock the source target, run all the things using Glue. This is where we need a bigger cluster, and hence we're going with Glue, not Python shell. And finally, so these are the three areas where we were on ECS. Now with serverless, we are even going beyond having to stand up our ECS node. Instead, we just go straight and use Python shell. The next thing that we do using Glue today is profiling. Now that we have data in Parquet format in our process data transactional layer, we want to profile this data. We want to know how many records came in, what are the data types, what are the various min, max, standard deviation of each. Again, the ML packages in Glue, Spark, they help you do all sorts of descriptive statistics. And those get written out again into S3. So whenever we run the descriptive statistics, put that into S3 as well. And once the Glue crawler has gone through this new data set, it appears as an Athena table. And in front of that, we have Tableau, so people can actually quickly go in and see how the profile data that we just brought in looks like. So not only do we use Glue to actually move the data, transform the data, but also so that we can profile the data and have the output accessible. So the way we look at Python shell, we look at AWS Glue for what it is. It's a serverless distributed compute cluster. So you use it so that you can process the data. We look at the Glue Python shell, though, as the edge node. Just like what we used to have, you used to have a cluster, and then you used to have an edge node from which you triggered jobs, where you did some of the light transformation, unzipping of files, tar extractions, small data sets being Parquet converted to a different data format like Parquet. So we see Glue Python shell fitting that particular mold, where we consider it as an edge node to a bigger Glue cluster. So that's how we think of it. So beyond just processing of data, why we exist at Realtor.com is to bring the best consumer experience to our users, and who we call consumers, and then connect them with the real estate agents. So for that, we have created analytical profile services. So we look at users, the clickstream that they generate, the listings they have viewed. We bring that together to create an analytical profile for every consumer. So for every cookied user or signed-in user, we go in and we say, OK, these are the events that they have performed within the product. These are the listings they have viewed. So that we create a batch profile every few hours. And for that, we use Athena to do the CTAS of Athena to build that out. However, from that, the serving layer is on DynamoDB. So to move data between S3, where Athena has brought it in, to Dynamo, what we do is we use AWS Glue ETL. And once the data, the batch profile, is in Dynamo, what we also have is we have clickstream coming in every 5 minutes on S3. We have an AWS Glue ETL, which is running near real time and updating the consumer analytics profile. So you have the batch, which tells you have seen these homes. And then as you progress, the near real-time Glue ETL keeps on updating things in Amazon, so in Dynamo. So that's how we keep our consumer analytics profile updated. And this is the basis of multiple solutions, data products, like personalization, being able to predict user behavior by looking at their history and their profile, what they have done in the past. So having said that, when I look back, what have been the benefits of using AWS Glue? First of all, the speed of implementation has gone up. The developer productivity, because we have a lot of inbuilt transforms. So for the explosion of multi-valued attributes into multiple rows in child table, for that UDF, we had 200+ lines of code that we had to maintain. Now with the relationalized transformation that's available in Glue, it's less than 10 lines, and something that we don't manage. The operations team, they love the serverless aspect of Glue. And finally, we found that the performance boost that we got for pushing into DynamoDB was very significant, things that we could get about a 10x improve in performance. Of course, we helped by finding the sweet spot of how much it can push through, have multiple Glue jobs running at the same time, and partitioning the input data set. But regardless, about a 10x improvement. Finally, I would be remiss if I did not acknowledge the engineering team, my team that has actually worked on these things in the last year, as well as the Amazon team, the account team, as well as the product team for Glue and the engineering team for Glue, for actually helping us through this whole adoption process. Thank you very much.
So we're happy to take questions now. And at 3:45, the two of us, as well as one additional speaker from 3M, will be happy to answer questions at that time as well. Go ahead.
How much local disk do you get in a Python shell?
It's a great question. I believe right now you don't get much. So the question was how much local disk you get in a Python shell. I think right now we're giving you something like 6 gigabytes of local disk. Depending on how how this varies, we might actually end up bumping it up. But we need to get some feedback from customers before we get an idea of how people will use it. Go ahead.
Is there a reason you guys didn't use the job performance feature in AWS Glue? You built your own blocking and updates?
Yeah, so the question about why we had to build the orchestration and other things around it, reason is we had already started before Glue's orchestration became. So now we use 2 features of Glue, the crawler aspect of it, the metadata, the transformation. The next step would be the orchestration.
Go ahead. Can you speak up? I only heard PII. I'm sorry. Can you?
Why don't you come over?
Okay. Oh,
How do you classify the data that is going into the data lake?
yeah.
We have very little personalized data. It's mostly cookied users, so based on the cookie ID. However, we do have some amount of information about logged in users who have signed up. And for that, there are several requirements. Like there are certain attributes that we cannot use for targeting, so we do not bring that into the profile. We just suppress those even before it goes into the profile. First name, last name, email is fine because they've signed that. They've allowed us to use it, yeah.
So I see a lot of use for ECS for Python scripting that runs longer than a Lambda used to, right? So it's interesting that you use the change to Python shell inside of Glue. Do you expect to see similar? I assume it's easier to develop on, much easier than having to do with Docker, maybe?
Yeah, so we have looked at ECS, we have looked at Docker, but this one works right out of the gate, so why even bother? And not very expensive either.
Do you expect to see operational type things move into Glue that maybe not big data, where they
Yeah.
run scripts?
So for me, it's the edge node. It's where I have to prep the data before I actually do the processing. So this is clearly that.
Yeah, so let me just add a little bit to that. The intention around Python shell was to, fill in the gaps where, the existing infrastructure for just doing the ETL was just too heavyweight. It's a generic programming environment, so I expect people to use it in all kinds of different ways. We are not going after the particular points in the space where say Lambda and ECS are going after. ECS, you can give whatever container you want to them. With Lambda, it's again a different set of additional programming languages, as well as spin up and shut down time and various other restrictions that are there. So we're going after a different point in space. One is large. There is literally building applications on the cloud. We are really focused around how do we enable ETL, right? And data lakes. Sorry, go ahead.
So we did a POC for Glue, and a lot of the things that were problematic for us in terms of orchestration, I think you guys can sort of cover here. But one thing that I was looking for and didn't see is we in our design we wanted this idea of a crawler per data source, which meant we would sort of kind of push the limits of the number of crawlers that we would be allowed to use, the number of jobs, et cetera. How do you respond to that?
Yeah. So the question is roughly around scalability of crawlers. So there's one point that I talked about in terms of the number of files and partitions you can handle, but there's another sort of axis in crawlers, which is the number of sources and number of targets that you can go after. And we have some workarounds right now that help you pack targets into a crawler. So crawlers do not have a limitation on the number of sources and targets that you have, though you only get one type of trigger with the crawler. So if you want different types of triggers, you have to have different crawlers. All of these limitations are slowly going to be removed. The ultimate vision, we're not there yet, is you just tell us what you want to crawl and when you want it to run, and you don't have to do anything else. Right? There is no limitation on how many machines and DPUs that are with the crawl. All that stuff gets kind of hidden away for you. We're getting there in steps. It will get better, but I'm happy to kind of talk to you, offline to help you kind of figure all that stuff out. Yeah. Give me 1 second. There was somebody over here. Okay, go ahead.
So when you're doing these kind of like transformations, graph data is landing in the same format. The size of that data is important for how long that job becomes. Does Glue or did you guys do anything to handle cases where that size changes dynamically based on what's in
Great question. So for us, in terms of what we have seen in terms of the performance, we have the DPUs, number of DPUs that we start the job with, and operations team keeps track of whether we need to bump that up. In what you saw from Mehul today about right-sizing the cluster in terms of DPU, now we have added insight into how it's performing and what should be the actual number of DPUs that we submit the job with.
Okay, we have time for one more. Sure. So that means that when our customers leave, we are compliant with GDPR. There's another level of GDPR compliance, which is when you are running on top of us and you want, when your customers leave, you delete the appropriate things. Those components are not there yet, and those you have to build on top, right? Okay, thank you guys.
Thank you.
There's going to be a meet the speaker session at 3:45 later. I think it's on your schedule. I'll be there, Arup will be there, and also Timothy from 3M will be there. Please join us at that time.